Hi, and in this laboratory we're going to explore Ohm's law. And we're going to do this by building a simple circuit and then adjusting the voltage and see how the current changes as a result of changing that voltage. Now remember, voltage means a change in potential difference, right? So we're going to supply energy to the electrons as they flow through the circuit. And as they move through the resistor, they're going to lose that energy, okay? And that is how loads, or in this case a resistor, actually would dissipate the power. Now the power in the resistor, our resistor, is mostly going to be dissipated as heat. But if we had a light bulb per se, then some of the energy would be lost to heat, some of it would be lost to light, so on and so forth. So what we have right here, this is a typical resistor that you might be able to buy from Radio Shack. I know it might be hard to see, but this is essentially what a simple resistor looks like. Now we're not really concerned about what the resistor is made out of. All we're really concerned with is that the resistor is going to mitigate the current. So what we have here is an adjustable power supply, adjustable voltage supply, and we're going to use this as our quote-unquote battery. And this resistor has a resistance of 475 ohms. And this little device, okay, is an ammeter, and it's going to measure our current. Now there are several different types of ammeters. More modernly, we use a digital multimeter, which will allow us to measure voltages, resistances, amperages in DC mode, amperages in AC mode, and then voltages in AC mode as well, right? And we'll show you how to use these things, but for the moment, I want to give you an introduction into circuits themselves, right? And so what we're going to do is I'm going to build a very simple circuit. We're going to adjust the voltage, and we're going to see how the current changes. Now, the voltages on this power supply are given as 3.3, 4.5, 4.5, 6, 7.5, 9, and 12, right? So I'll write those on the board. Was it 3.3? Yes. 4.56, 7.5, 9, and 12. All right. So there are the voltages. And what we're also going to do is we're going to check that the voltage across the resistor, okay, also stays in step with the voltage from the power supply. Now, in a very simple one resistor circuit, that should be a one-to-one relationship. So whatever the voltage supply is providing, that should be the voltage lost across the resistor. Okay, so what that means is the resistor voltage should read the exact same voltage in magnitude as the power supply. And we'll see if that's true. But first, let's set up the circuit. So right now the power supply is off. You should always have electronics are off when you're building things. And we've already got one of the wires running from the power supply into our ammeter, and the other wire connected on the other side of the ammeter. And so basically, if I were, and I'm actually going to unplug, practice what I preach and unplug this just to be on the safe side, because you never want to do this in real life. Okay, you never, ever, ever want to do this in real life. Current needs a complete circuit to flow, a complete path to flow. So if I were to connect these, you can see that I now have a complete loop for the current to flow. Now, according to Ohm's law, V equals IR, because these wires have very little resistance, okay, they essentially have zero resistance. Very short wires that are good conductors essentially have zero resistance. So your ammeter as well is also built to have very little resistance. Your ammeter, you don't want it to interfere with the circuit itself. So your ammeters are built to have very low resistance as well. So effectively, this circuit essentially has zero resistance. So if I wanted to calculate the current using Ohm's law, the current is going to be I equals V over R. But if R is really small, then that means I becomes really big. That's called a short circuit. So you get a lot of current, a large amount of current with very little resistance. Okay? So that's why we actually use resistors, to mitigate the flow of that current. So all I have to do is insert the resistor into the circuit. And now I've got a complete path that's going to flow into the ammeter, through the resistor, and then back into the power supply. So there's my complete circuit. It doesn't exactly look like a loop per se, but it really is. Okay? It really is a loop. Okay? It's just a complete path for the current to flow through. So I'm going to plug this back in. And what I'm going to do is turn my power supply on, and you'll notice immediately that the needle on the ammeter jumps, right? The needle on the ammeter jumps. And I'm going to actually take pictures because I know it's hard to see in the video. So I'm going to take pictures at each of these individual voltage settings of the current so we can actually then use Ohm's law, all right? But if I go up to the next setting, you can see, whoops, jumped one. You can see that the needle jumped a little bit. Next setting, next setting, next setting, next setting, and next setting, right? So the needle is going to move based on how much voltage we put into the circuit, okay? And to also prove that the voltage will jump in turn, okay? Now, one thing I should mention, the ammeter here is placed in a position in the circuit in what we call series. It is in series with the current. It means that the current is actually flowing through the ammeter in the closed path, okay? So it's actually part of the closed loop. When I insert voltmeters, okay, when I insert a voltmeter, I need to insert it in a way that we call parallel. Now, in parallel circuits, generic parallel circuits, current can flow. But a voltmeter is designed such that its internal resistance is extremely high. Okay, the internal resistance of a voltmeter is extremely high. You don't want it drawing any of the current away from the ammeter. You won't get an accurate reading if that's the case. So to do this, to put the voltmeter in parallel, all I'm going to do is clip the leads of my voltmeter wires to the ends of the resistor, like this. So now what the voltmeter is going to do is going to register the voltage that occurs on either end of the resistor. So as the current is flowing through the resistor, it's going to lose its energy inside the resistor. So when the energy is on this side, it's going to be different than this side, and you get the change in energy. And remember that voltage is energy per unit charge. So if I have a change in energy per unit charge, that's equivalent to a voltage. So the voltage that the resistor absorbs or essentially dissipates is going to be equal to the voltage of the power supply. Conservation of energy. The energy that goes into the circuit from the power supply has to be the energy used up from the resistor. You can think of this type of circuit current setup like a waterfall, right? So if I pump water up to the top of a mountain, that is what's happening with the battery. And then as the water flows down the mountain, it loses that potential energy. That's the water flowing through the resistor. And then when it hits the bottom, it gets pumped back up to the top, falls, pumped back up to the top, falls, and so on and so forth. And that's a rough analogy for how you can think about current and how the energy actually does get used up inside the resistor. Okay, but so now watch the voltmeter needle, and you can see, you should be able to see. This was working just a minute ago. I'm going to pause the video, troubleshoot, we'll be right back. We're back. So I figured out what was wrong. I had the wires on the wrong end and the needle was trying to push the other way. So as you can see, I'm on the first setting, so the needle should be just a little bit above the 3 mark. And again, it may be hard to see, but it is. And as I move up through the settings here, the voltage needle definitely jumps, right? The voltage needle will definitely jump. So it's going to be a little bit tough to show the voltage for every individual measurement because this goes up to 12 volts while my voltmeter here only goes up to 10. But all of the other analog voltmeters that I have are 50 or larger, so it would be very difficult to see the incremental changes between these smaller numbers on that scale. So we will actually use the digital multimeter for that measurement when the time comes, right? But the bottom line, what I want you to do is I'm going to put the voltmeter, or I'm going to change the voltage rather from the battery on these different settings and take pictures of both the amperage and the voltage, and I want you to plot those using V equals IR, okay? We're going to plot those using V equals IR. Plot your voltages on the y-axis, plot your currents on the x-axis, and the slope of that should give you the resistance. Now, a good scientist will see a slight flaw with this, okay? Typically, we want to put the independent variable on the x-axis, which in this case is the voltage. The independent variable is the thing that I can control. And the dependent variable, in this case the current, is the thing that responds to that input. So if you want to, and we will actually do this after we do it the first way, what we'll actually do is then plot the current on the y-axis, the voltage on the x-axis. You'll still get a straight line, okay? You'll still get a straight line, but that slope will now represent the reciprocal of the resistance, okay? And let me describe what I'm talking about here. So we know V equals IR, right? And this is a linear equation, okay? That is a linear equation. This would act as Y, and I'm going to actually rewrite this as RI, right? Y equals mx, okay? So this has the form of Y equals mx, where V is Y, R is your slope, and I is your x value. So that's why initially we're going to plot it, V on the x-axis, or V on the y-axis, and your current on the x-axis. But in truth, the proper way to do this is actually to plot your independent variable on the x-axis and your dependent variable on the y-axis. And if you do that, you get that equation, right? You get this equation, and so now your slope is actually the reciprocal of the resistance. So that is what we're going to do also as well. And you can actually verify that you can determine the resistance in both cases using either method, okay? But technically, we like to put the independent variable on the x-axis and the dependent variable on the y-axis, okay? So that's the setup, that's what we're going to do, and I will take these pictures so that you can actually then plot the data, and hopefully you'll get a linear line. And the linear line in the first case should be 475, okay? You should get 475. Now remember, this is in milliamps, okay? This is in milliamps, so you want to convert this to amps, okay? So you're going to need to divide by 1,000, okay? You're going to want to divide that number by 1,000 and use that in your plotting, okay, when you plot these numbers, okay? So that is what we're going to do, and I will see you next time.